Okay, in this video we're going to go through some of the two-star questions. Not all of them, as they are a bit longer, but we'll try to get through as many as we can in about 20 minutes or so. So let's start off with question 25, our first two-star question. We're told the figure below, 13.36, I'll let you look at the textbook, shows transverse waves being generated at the rate of 10 per second. From this diagram, determine and asked for amplitude, wavelength, period, and velocity. So the first part is to think about the number there that's given in the text. It said 10 per second. Well, the per second, remember, is frequency, or hertz. So that means that we must have an F equals 10 hertz from the text. And notice that it also hasn't actually asked for frequency, which is a pretty common thing to be asked for. And since it hasn't been asked, it's a pretty good assumption to think, okay, well, I've got to find it from the text. Okay, so question A is asking for the amplitude. Now, if you're looking at that diagram, remember it's the distance from the midline, the x-axis, to a maximum displacement. And we can see that it goes up to 4 centimeters according to the units, or down to negative 4 centimeters. So amplitude is 4 centimeters. B, we're asked for the wavelength. Now, wavelength, remember, is the length of one repetition. So if we start from the x-axis at 0 and we follow it through, not till the first time it gets to the x-axis, but the second time, so where it repeats the full cycle once and then goes back to go back up again, we see it crosses that point at 20 centimeters. We can also check from crest to crest. Our first crest has a peak of 5 centimeters, our second crest has a peak of 25 centimeters, that difference is 20 centimeters, so lambda equals 20 centimeters, or 0.2 meters. We could turn amplitude here into 4 times 10 to the negative 2 meters if we wish to as well. C. Period. Well, we can't read period off this graph. We have centimeters on the y-axis and centimeters on the x-axis, so there's no time to interpret. But we do have a frequency that's been given to us here. So we know the relationship between period and frequency is an inverse. So 0.1 seconds. Okay, and the last part of the question is asking for the velocity. Again, we don't have time, but we do have the bits we need. We've got our frequency, we've got our wavelength, so let's use our wave equation. V equals F lambda. V equals 10 times 0.2 equals 2 meters per second. Okay, let's see, and the textbook gives that instead. Oh great, it's giving in SI units, which is what we want. Okay, let's head on to 26. Now we've got a bit of a story here in 26. When earthquakes occur, they create waves that spread outward from the source. 3 types of waves occur. Primary, or P waves, which are caused by back and forth movement of rocks. The secondary, or S waves, which travel as a result of the up and down movement of rocks. And the L waves, which are ripples that travel on the surface and are set up when P and S waves reach the surface. The L waves cause rocks to vibrate in an up and down motion. First question is asking us, well, what type of wave? So again, remember we've got longitudinal and transverse. So let's see, we've got P waves, S waves, and L waves. So in this case, we've got to interpret the text. So primary P waves caused by back and forth movement of rocks. So the direction of oscillation is in the direction of movement. Okay, because if you think a wave starts at a point somewhere deep inside the earth and then travels outwards to the surface where we might feel it, if it's backwards and forwards, that means it's going that direction, which means that it must be a longitudinal wave. Our secondary wave, S waves, travel as a result of the up and down movement. So this would be up or down. So let's label that P, let's label that S. So this means that it must be a transverse because it's acting transverse to the direction of motion. Now finally, L waves, they're told that it causes rocks to vibrate in an up and down motion. So see, we've got that language there. So it's on the surface, that's where it goes up and down. So that also must be transverse. Alright, now the second half of this question, we got a bit of math instead now. So we were told earthquake waves have a wavelength of 10 meters and a speed of 3 kilometers per second. So let's categorize that. Wavelength, lambda equals 10 meters. And we have a velocity of 3 kilometers per second, or 3 times 10 to the 3 meters per second. Now, I know some other questions we've seen, I have left it in centimeters to work with, which isn't too much of a drama, because if I've got centimeters and seconds, my answer will be in centimeters per second. But here, because I've got meters for one and kilometers per second here, well, that kilometer and that meter won't work together. I did need to convert that to meters per second. We're asked to find frequency. So again, we can see it's just our wave equation. So F equals V over lambda equals 3 times 10 to the 3 divided by 10, which should equal 3 times 10 to the 2 meters per second, or 300 meters per second. Okay. Oh, sorry, we were talking about unit hertz. Frequency, 300, or 3 times 10 to the 2 hertz. Always double check your units. You don't want to make that mistake. Alright, 27. Again, we're interpreting a figure here, so make sure you're looking at that. So figures 13.37, A and B. Alright, so we've got two waves. Show a transverse wave and a longitudinal wave moving to the right. Indicate the direction of motion of the points A and B. Okay, so if we have a look at that, this is a similar question to one of the ones we did in text before. So if we have a look at A, it's a transverse wave, so we know the points are going to move up or down. And if we have a look, remember, direction of motion is going to the right, so the particle will do whatever comes next on the left. So point A is going to go, point A is right at the start there. So let's see, point A for diagram A is going to go down, and B will also go down. Because if I just draw a wave quickly, and if it's going that direction, this point's going to go over to here, this point's going to go over to here, this point's going to go over to here, which means B would move down. And so again, we could say, oh, well, it's going to go back through there, and so this point will come over to here, and A will end up going down. Okay. The trick is that you tend to look at the diagram and go, oh, well, it's going up to the right, it's moving to the right, which means it must go up. You've got to think about what's going to come next into it. Okay, let's have a look at our other diagram though. This is a longitudinal wave. We haven't done one like this before. So A and B we can see are either side of a compression. Okay, so we've got our spread out bit, and then a compression, and then a spread out. That was just wonky there at the end. Then a spread out bit, a rarefaction. It's very hard to draw these waves. So point A here, point B here. So this point at the moment is squished together. So the next thing that's going to happen is it's going to spread apart. So if we assume that, then A must move to the left, and B must move to the right. Okay, let's look at 28. Alright, so we've got another diagram here. Waves are sent down a set of connected ropes and later returned to the sender as shown in figure 13.38. What is the relationship between the density of the rope, sections A, B and C? Well, let's draw this one out. This is pretty simple to draw. We've got a nice big wave approaching a connection to another line. I'll just draw that one a little bit lighter. And then that's connected to a very heavy line. Let's draw that one in a bit. So this is section A, section B, section C. Now, it's very tempting with things like this to go, oh, well, this is drawn heavier than this, so this must be more dense than this, and this is drawn heavier than that, and it's drawn heavier than that, so C must be more dense than B and A. Now, we don't know. we're not doing a drawing class, we're doing a physics class. So we have to look at what phenomena we can observe in order to figure out, well, what actually is happening here. So I'm going to draw the reverb. So first bit, again, then B, and then C. Alright. C, B, A. Wave is going that direction. That was wonky. Wave is going that direction. Wave is going that direction. Okay, so what do we know about reflections? So remember, we've got a wave travelling from one medium to another in our starter, and in our second time phase we see it's come back, so it's had to reflect. So which wave came first, this wave or this wave? Well, we might want to think this wave because it's closest to the right, but this wave must be the first one because when this hits, a wave is going to reflect. Okay? And then if some of it passes through and hits here, then a wave will reflect again. So if we're going from A to B and reflected back in phase, that must mean that A heavier than B. And we'll call this pulse 1, we'll call this pulse 2. And again, they're not labelled on there, but there's no reason you can't give it a name if you're answering a question like this in an exam to help you explain your methodology. It's a really good way to help with your communication because 1 in phase with, let's call this one 0. That is a very terrible looking 0. Okay. So what would have happened is that it would have hit B, some of it would have gone back. Let's draw that actually. And some of it would have continued on, but less. C, B, A. Now, this wave's just going to go off that way. We don't care about that anymore, but this wave would have continued on. And it would have hit C. Now we don't see any wave in C, so it all got reflected. That means that C must be pretty heavy or perhaps solid. But our second wave is upside down, which means that this had to get reflected and reversed, which definitely tells us that C is heavier. Okay, so C heavier than B because 2 outer phase with 0 and 1. When this wave would have hit here, because it's going from a what's what I'm looking for? A light mass to a heavier mass, but it's still a rope that we know can transmit a wave. It got passed on. Some of it may have got bounced back, but we're not seeing that there. So we know that A is heavier than B, and B is definitely a lot lighter than C. C might be heavier than A. We don't know. There's no relationship that we can establish by looking at that. I probably would have expected maybe a little bit of a wave to come back here, back in phase with the original wave with B, just to, because if that's going to pass through, some would reflect back. Not a lot, but perhaps a little bit. That being said, this still makes sense. So it's all about, well, in that case, what were the reflections, and hence what were the boundary conditions like. Okay, question 29. We have a lovely diagram there with a lot of points with a standing wave. Now, it kind of looks like a whole bunch of eggs, but I'm going to redraw it because it will just help clarify the picture a little bit more. So we've got our wall, and we've got our middle line. Let's make that a bit longer actually. So I've got 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Now I've drawn that one in one colour. I'm going to draw the other half in red because the picture is kind of confusing. It kind of just looks like, oh, the wave's in two places at once. The wave isn't in two places at once. The wave is going the black phase and then to the red phase and then back to the black phase and then back to the red phase, and so it just keeps oscillating between the two. Okay, and we're labelled A, C, E, and so on. You can see from there. So it's asked us, well, what is the wavelength of the waves? So wavelength would be crest of one wave to the crest of the next. Not the black one, because the black one is when it comes back the other side. Or we can go from the first middle point to where the red would repeat, or where the black would start repeating. So we could say that A to E is a wavelength, or C to G. We could also go B to F. Lots of different ways you could indicate a wavelength on this. There are many more. B, which points are nodes? Now remember, node means no movement. It's not something we cover in this unit, or at least it's not something we cover in the geometric light unit. It's something we cover in the medical physics unit. So whenever you're watching this video, you may need to know this, or you may not. So if you're doing telescopes with me at the moment, you don't need to know about this. So what points are nodes? Nodes means no movement, okay? Which means, well, A is right in the middle, and so C, and so is E. So A, C, what did I do there? A, C, E, let's see what's the next one, G, I, K, are all nodes. Node meaning no movement. So anti-node must mean the opposite. Well, it's whatever we didn't just list on that question. So we've got B, D, F, H, J, and L. Okay, D. Now I'm going to do a little bit of mathematics. So the distance between A and F is 5 meters. What is the wavelength? Okay, so we've got there, and F in this case is at this anti-node. So it's a little bit more than one wavelength. Well, how much more? We can see that, well, this would be one wavelength, that would be two wavelengths, so that would have to be 1.5 wavelengths if we went to G. So F would have to be 1/4 wavelength, 1 1/4 wavelengths. So we know that that distance is 5 meters equals 1.25 or 1 1/4 wavelengths. And so if we rearrange them, we get that lambda equals 5 over 1.25 equals 4 meters long. Okay, it's a proportionality thing, it's not a special equation thing. Okay, question 30. Figure 13.4, which is off to the left there, shows a wave in the same section of a string at 2 different times. What is the greatest possible period of the wave? Okay, let's draw this. We have 2 waves. Our first one is there, and our second one is there. So we've got 1 1/4. So it's going to be 1/4, and that will be 1 wavelength. This seems to have 1 1/4 wavelength as well. We want to know what is the greatest possible period. So here we have t equals 0, little t, sorry. T equals 0, here t equals 0.1. Okay, so we want period. What's the definition for a period when we talk about time? A period is the length of time taken for 1 wavelength's worth of motion to happen, which means that 1 wavelength repeats itself. So if we look at this, it would be the time it takes for this point here to get to this point here, or if it's going the other way, because we're not told what direction it's going, this point here to get to that point there. So we need to look at the 2 images to try to figure out, well, how far did this thing actually go? Now remember, we're after the greatest period, which means we want the slowest possible wave. Okay, well, how do I know it's the slowest possible wave? If we think about the wave equation, we said that v equals f lambda, but f is the same thing as 1 over t, so v equals lambda over time. So if we want this to be really, really big, this must be really, really small, because we can't change the wavelength is fixed in this case, but these two things are inversely related. Okay, so that's a little way to sort of mathematically think about, well, what direction do I need to go. So if I go from this side to the left, okay, so if one wavelength goes that direction, or in the 0.1 seconds it goes that direction, because this bit here would have to get to this point here. Well, that's a lot further than if we went the other way. Here we'd only have to have this point here going to this point here. It's only moving a quarter of a wavelength there. Okay, so it's a lot shorter. This one moves one whole wavelength in 0.1 seconds. This one moves only a quarter of a wavelength in 0.1 seconds. So if it's only moving a quarter of a wavelength in 0.1 seconds, it's a lot slower than one wavelength in 0.1 seconds. I think we can hopefully understand that. If not, ask me in class. So that means it has to go that way. So this is going to be wrong. This would be right. Okay, so if it's moving a quarter of a wavelength in 0.1 seconds, well, how many quarters fit into a whole wavelength? It's going to be 4, so we have to multiply our time by 4. So t equals 0.1 times 4 equals 0.4 seconds. Now, I actually don't agree that that's the greatest. That's what the textbook gives you as the answer is the greatest, but I don't agree it's the greatest because, well, what if it just moved? Actually, no, that will be right. Ignore that thought. So that has to be the greatest possible. I was thinking of frequency for a moment then. So let's head to 31. I think we'll finish off the video on 31. So a transverse wave is travelling from right to left through a series of particles. At a certain instant, the waveform is shown in 13.41, which is the diagram below it. Each of the vibrating particles is observed to perform 2 complete oscillations in 20 seconds. So 2 oscillations in 20 seconds. Okay. So then, well, how long for one oscillation? That would be 10 seconds, so that must be a period, because we're finding out, well, how long for one oscillation. Or we could divide it down, 2 divided by 20, and get frequency. Either would work. So we want to find the following quantities: wavelength, frequency, amplitude, and speed. So let's start off with that. Wavelength, well, that's going to come from the picture. If we have a look, we see that each square is equal to 4 centimetres by 4 centimetres. So A to E would be our wavelength, which means that we're going to have 16 centimetres. So 16 centimetres. We could turn that into SI units or leave that as that. Okay, next part of this. Frequency. Let's label that first. Lambda equals 16 centimetres. Frequency equals, well, we want to know, well, how much per 1 second. That's going to be 2 divided by 20 equals 0.1 hertz. Okay, next part, amplitude. So for amplitude, remember, we just need to read off the question itself, or the diagram itself. We want to know the distance from the middle line, and the middle line has the points A, C, and E on it, up to one of the maximums or minimums. So it looks to be 1 square from C up to D, or C down to B, which means that the amplitude must be equal to 4 centimetres. Speed. So now we want velocity. Well, same as before, velocity equals F lambda equals 16 times 0.1 equals 1.6 meters. Oops, not meters, sorry. Centimeters per second. Okay. At the instant shown, which of the particles A to H are moving upward, downward, or momentarily still? Okay. Oh, excuse me. Let's do that. B1. So which ones are going upwards? So direction of wave motion is to the left this time. So we want to know, well, whatever's to the right is what's going to happen next. Okay? Oh, sorry, no, we're asking about the instant. So what movement would they be doing right now? So upwards, we're looking along our middle line, or at least we're not looking at our peaks and our troughs. Let's see. Where did they just come from? So if we look to the left to see where they just came from, so to the left of A is upwards, which means they have just come from up, so they are going down. And they will be going down next. B is going to be momentarily still. C just came from being down, so the next thing that will happen to it will be to go up, which means right now it must be moving up. The next one, E is going to be just came from, so it's moving down. F will be moving down as well, and H is similar to C in terms of where it is, so H will also be moving up. It's just come from that position at G, so it's going to keep going up next. 2. Which ones are going downwards? So I believe I said A was going down before, because it's just come from an upwards position. E will have to as well, because it's one full wavelength away from A. And F will move downwards as well. Let's see, where's our next bit? Oh, momentarily still. Okay, so well, that's going to be anything at a peak or a trough. So B, D, and G are all going to be momentarily still at that point in time. Okay, so what will the position of particle C 1/4 of a period of later be? Okay, that's a mouthful. So particle C, let's draw our wave for a moment. Particle C, we've got motion going that way. C is here. 1/4 of a period later. So if it was a whole period, it would be, I'll just do these in another colour. After 1t, C would be there. It would be 1 full wavelength later. So that means after half a t, it's going to be half a wavelength later. So 1/4 t must mean that it's going to be at the peak. Since it started at the mean line, it will end up at our peak. Okay, and because direction of motion is going to the left, if direction was going to the right, it would be in the trough. So if we see that from the picture that it's 4 centimeters for 1 square, so therefore the displacement equals 4 centimeters up. Alright, we'll finish off this video for there, since the next question is 32, which was a 1-star question, and I'll pick them up in a little bit. Thanks, guys.